So tonight we have with us Dr. Poonam Chandra. Okay, good. And so she's going to talk about the restless universe, and I'm going to let her go through all that stuff. But let me just give you a little bit of background for her. So she is currently working at NRAO right down the street, right? Do you have a card, by the way? Did you get up here?
Yes.
Yeah, okay. Last month we didn't realize that Dr. Eibenstein didn't have a car. And so, but we got her back down again, but I felt bad. Anyway, so she's in NRAO. She's completed her Ph.D. at Tata Institute of Fundamental Research in India. She was later a Jansky Postdoctoral Fellow at NRAO at UVA from 2005 to 2008, and was a Senior Research Associate and an Adjunct Assistant Professor at the Royal Military College of Canada until 2012. Afterwards, she was at the National Center for Radio Astrophysics at the Tata Institute of Fundamental Research. Am I saying that right? Tata? How do you say that?
Correct.
Close enough? All right, sorry. And let's see, she's a faculty member. And in May 22, she joined NRAO as an astronomer here. And so with that introduction, Dr. Chandra, over to you. Now, we got to get your computer. No?
That's fine. I can just use this.
Sure.
Yeah.
Or Teddy would be happy to.
That's fine. I'm quite close to this, so that's okay.
Oh,
All right.
that-
Yeah,
right.
sorry about this. I hope it works. And
Again, Dr. Poonam Chandra.
all right. It's my pleasure to be here, and I should already say that I'm not an optical astronomer, so I actually don't know most of the, I don't know how to observe with a real optical telescope, and we don't get to observe with X-ray telescope, so I don't know how to observe with the telescope that well. But I'm going to tell you a fascinating story today. And the story is about a gravitational wave observatory. Well, it doesn't move. Okay, I don't know why my slides are not moving, so I don't know what happened. Did we do something by hiding it, or? No, it's not.
Hey, Dr. Chandra, just for the record, it's not my fault.
Yeah, so I think we just need to do is exit that annotation layer and then hopefully.
Oh, okay, good. Okay, let's try this again. So this is LIGO gravitational wave observatory, and we have two of these, one in Livingston in Louisiana and one in Hanford in Washington State. And it, of course, detects gravitational wave, and it has two mirrors. These two arms of LIGO are 2.5 miles in length. And on 17th August 2017, one of the arms changed its size by 1/10,000th of a width of a proton. If you cannot imagine that, take your hair, take the width of the hair and cut it in 1,000 trillion pieces. And one of that was the change in the arm length of LIGO. And that was considered the watershed event of the century because, let me just see if I can move this. My titles are not coming, but that's fine. Let's just go ahead. At least quarter of the professional astronomers on this planet worked on this event. More than 100 telescopes observed this event for days to months to years. And finally, more than 100 papers came out, but the main paper which came out had 4,000 authors. And I think the author list is several orders of magnitude larger than the paper itself. But this is what the event was. And with handful of physics laws under our belt, observing gravitational waves and some photons in different electromagnetic wave band, what we had figured out that we were seeing merger of two neutron stars, which was emitting gravitational waves and light. And this event had happened when the dinosaurs were still ruling the earth, 144 million years ago. And the gravitational waves had taken that much time, 144 million years, to reach to Earth on 17th August in 2017. And by understanding some physics, we learned that these two objects which was merging were neutron stars, which are so dense that you put one sun in 10-mile radius, which means if you take one spoon of that neutron star, it will weigh 1 billion ton on Earth. So it's such a dense object, and that's what had happened. So this is the story, and to understand that, I want to go back and retrace my steps and try to explain what actually happened and how did we detect this.
Hey,
So let's,
just a quick question. So was this the first time we observed a gravitational?
so we did observe the first gravitational wave in 2015 on 14 September. That was from the merger of two black holes, but black holes don't give out photons. So we didn't see that in with the telescopes. Yeah. So, okay, so now let's just understand this. So if you take a star cluster and wherever in our Milky Way, star clusters are the one, lot of stars made from the same nebula. So they all have the same age, but they have different masses. If you rearrange in terms of increasing intensity and temperature right to left, you will see that they don't occupy random spaces. They occupy this very well defined, which is HR diagram. And I now realize most of you know about this diagram. Our sun is a very average star, which lies here. And the sun is fusing hydrogen into helium. And that fusion gives rise to energy, which is keeping us alive. And this is the reason of, we are here. But once after 4 billion years later, when all of the hydrogen will be consumed, the sun will increase in size, become a giant star, and then leave its outermost layers as planetary nebula and become a white dwarf. So that's the fate of our sun. But that's not what I'm talking about. I'm talking about the massive stars, which are at least more than 10 times mass of the sun. And these stars also undergo fusion, but the fusion is not just hydrogen into helium. They have enough temperature and density that even the higher order fusion reactions take place, and they end up making carbon, neon, oxygen, silicon, iron. And when they run out of their nuclear fuel, no more fusion happens. At that time, and even before that, during this evolutionary process, the star becomes, it comes in this part of the chart diagram. And one of the example is Betelgeuse. And just to give you an idea of the size in our solar system, if this is the size of our solar system, the size of the Betelgeuse will be as big as orbit of Jupiter.
Wow.
So that's how big these supergiant stars are. And at some point in this evolutionary stage, the star will run out of its fuel and explode as a supernova. So that is how, as of now, we understand the end of all the massive stars in our universe. They live much shorter lives, not as long as sun is going to live, like around 10 billion of total lifetime, but much shorter lives. But they have much more exotic, much more restless processes going on, and a lot of extreme physics going on. So, and this is very important because in the massive stars, when all of these things or fusions are happening, this is actually the only sites in our universe where these heavier elements are being formed. There are no other sites where oxygen is being formed, which we are breathing right now. There are no other places in the universe where iron is being formed or aluminum is being formed, which is in our cars. So it means we do know that when the Earth was formed or the solar system was formed 4.5 billion years ago, there must have been many, 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 many massive stars which must have died and scattered these heavier elements in the medium, in the interstellar medium, so that when the new stars were formed, they already are, the sun was formed, it already had the heavier elements which we see on our Earth. So we certainly have that idea, and I'm going to tell that that's just part of the story, and the next story is going to come soon. But I wanted to get into another kind of explosion, and this is gamma ray burst explosion. It is roughly same as supernova, except that all of this energy and ejector explosion is not happening spherically symmetrically, but happening in these collimated jets. So we get to see them only when they're looking at us, that is looking at Earth. And since they are just a few degrees in size, and all of the above energies coming in this, they are much more, way more energetic when they come to us than a supernovae. But that also means that we see much fewer jets because we only see the ones which are looking towards us. So if we see one, we know that we are missing out at least 500-600 more such gamma ray bursts. So we see around 1, 2, or 3 per day these days with our observatories, but we see a lot of supernovae. And if you calculate the rate of supernovae in our universe, around 8 to 10 supernovae are exploding every second. So that's how much supernovae explosions are taking place. These are the only sites in astrophysics or in the universe where we can study extremes of physics, and we can understand our physics laws, and we can see whether the physics which we understand sitting on Earth, whether the physics applies to these extreme conditions or not, these extreme amount of energies. Because one supernova, we were talking about so many stars and planets. If you take our Milky Way, which has 200 billion stars, this one supernova is going to shine brighter than all of those 200 billion stars together. And if you take the gamma ray burst, and as the name suggests, it's emitting mostly in gamma rays. If you take that gamma ray burst, they last only for 2-3 seconds, sometimes maybe at most a couple of minutes. In that little time, they will outshine the rest of the universe in gamma rays.
Wow.
It literally is such an exotic event. Now, the another interesting part is that the story doesn't end there. I think many of us know that there are these objects, neutron stars and black holes. As per our understanding, these neutron stars are formed as a compact remnant of supernova explosion. It means when the star is exploding, it is leaving a neutron star at the core. And if a gamma ray burst is happening, what we understand now is that they make black hole at the center. And those black holes, there should be a lot of such black holes in our universe, which is what we are seeing with LIGO. And you may have noticed that I'm just saying as per our understanding so many times, because the one of the biggest beauty of science is that we are always ready to be proven wrong. We only know what we know at this point, but there could be something else which can prove us wrong. So we are just trying to understand our universe bit by bit, and this is our current understanding. This is what it is. So now let's come to a more interesting part, is that when I'm looking at the sky, I don't see all of these things. So how am I actually telling you all of this? How do I know that all of these things are happening? How am I observing these things? So first of all, before going to that, I wanted to say that I wanted to come back to the gravitational wave event, that these neutron star I talked about and the black hole, the neutron stars, when they merge, they do create the gravitational wave, the watershed event I talked about. And we have only seen one event so far, which happened on 17th August 2017. But I should also say that last 2 weeks, I was really, really busy because LIGO had put out an alert on 18th of August. And they said that there is a possibility that there could be a neutron star merger event, and we were using all our telescopes to look at it. And after 1 week of observations, we figured out it's a supernova, not a merger event. But so this is the only event so far. This is just a neutron star merger, but black holes also merge. And black hole also, like this particular event give rise to energy of 3 suns in like a fraction of a second. So it's very energetic event, except that it doesn't emit any light, so we don't see them. So how do we understand all this? How do we study our universe is the question. And the first thing is that if we look at the sky, this is how it looks. This doesn't tell us anything. But thankfully, we have telescopes like Hubble, where this little piece of the sky will look so gorgeous with so many galaxies and exotic things. And when I'm talking of supernovae and gamma ray bursts, I'm always talking beyond Milky Way. I am not a single object. I'm talking as in our Milky Way. The last supernova in our Milky Way was 400 years ago. I think all of you know Kepler supernova. So we have not observed any other supernova. It hasn't happened. But anyway, so we look at with the optical telescopes, we create images, but that's not how supernovae are observed. We don't know which star will die at what time. We can't pinpoint a time. The star may die like right now or 10,000 years later, because in the lifetime of a star, this is all a very small amount of time. So we really don't know. So the way we look at these things, there are these robotic telescopes. I'm just naming some. They keep scanning the sky, the images you were seeing, and then there are softwares which keep looking for difference of image and if something new has popped up. And most of the time you don't see it with naked eye because they are very small magnitude, 16, 17, 18 magnitude objects. But the telescopes can see it and software can find these new sources, and then people do the follow-up observations, take the spectrum and try to understand. There are some very nice ground-based observatories in optical band which are being used for these kind of studies. Not just ground-based observatory, there are also space-based optical and infrared observatories. Of course, JWST is one, Hubble is one, and Spitzer and Herschel are no longer there, but they were also very useful when they were working. So we do this study with optical, but I have to say that optical is a very small part of the visible spectrum, really, really tiny part of the spectrum. But that's how traditional astronomy has been done. But the fact remains that if you only focus on optical, you are not going to get the full picture. When you have an event which is so far away and all you're getting a handful of photons, you may as well want to actually study as many ways as possible. And not just astronomical object, if you look at like human being, if you look at the person in visible light, infrared and X-ray, you get different kind of information. The one wavelength does not give you information about, say, optical doesn't give you information about the bone structure, or infrared, doesn't give you information about what clothes you're wearing or something like that. Similarly, the same applies in astronomical objects also. And this is the same object. This is Sagittarius A. And if you look at the radio band, optical, it doesn't look, there's nothing special in optical band. But if you look at the X-ray and if you look at the radio, it gives a completely different picture. So with that idea, we do try to utilize other wavelengths. So we build telescopes in other wavelengths to study these things. But things are not that simple, because if you take the radio wavelength, this is the moon with a 10-centimeter optical telescopes. Most of your telescopes are better than this telescope, and you get such a sharp picture of moon. And then you take a moon with the radio telescope, which is 350 meters in diameter, and that's what you get. You hardly get anything. And the reason is that the resolution is very important, but resolution goes as wavelength over diameter, and wavelength is very large for radio telescopes. So the only way radio telescopes work is you have very big telescope like Green Bank telescope, or they're all like several 100-meter telescope. But that's just not good enough. We need a 30-kilometer telescope or 300-kilometer telescope or 3,000-kilometer telescope, and you can't build that. You can't build a 30-kilometer dish. So what we do, we use what is called interferometry. The idea is put a lot of small telescopes and try to get as much information as possible. It's like hundreds of ants trying to study an elephant. And so all the ants should just study with the little parts and then try to correlate the information, cross connect, and then try to figure out how the elephant looks. But in building even these many dishes are very difficult. So what we use is called aperture synthesis. Just build some array and then we assume that the source is not changing in the next 7-8 hours when the Earth is rotating significantly, which means we keep observing, and then we have effective mirrors at all these positions. So this is how radio astronomy, where I work, is done, which is called aperture synthesis, and interferometers are used. And we have some, and these are very expensive, so we have only a handful of such radio telescope. One we have, of course, our biggest one is in, our best one is in Chile in millimeter band. Then we have in Socorro, very large array. Then there are these two telescopes, which are, one is Australian telescope, one at lower frequencies, and GMRT in India at lower frequencies. But NRAO is involved in upcoming next generation very large array, which is going to be at least 10 times more sensitive in every single aspect than the current telescopes. There's another very big project, square kilometer array. So this is a lot of new projects are coming in radio band because we get a very different perspective of our universe in radio band. But what about lower wavelengths or very high frequency or very high energy? That doesn't work that easily because I have to just, sorry, because our Earth atmosphere doesn't let all these things come to us, which is good, because if gamma rays and X-rays can penetrate, then that's, we can't take that. That's not good for us. But we want to study, so we want to put telescopes in the space, and there are some of these telescopes. Some are NASA-run telescopes, some are European Space Organizations and telescopes, which are carrying out these studies and making a big advancement in this field. But what about things which do not emit light? And that's where the gravitational wave observatories come. And just a very simple concept. The gravity in Einstein theory of general relativity is just a curvature of space-time. You may have seen those experiments where you put this sheet and then tightly, and then you put a object, and then you see this curvature. But then if you have two objects which are accelerating and very massive objects, then you create these ripples. These ripples in space-time is called gravitational wave. And these ripples are nothing but the space-time itself is causing these ripples. And the gravitational wave observatories, which are where these are the current observational operational ones, are just looking for these ripples in the space-time. So the way it works is that I was talking about these mirrors, and what happens, it's exactly the same distance. So when the light goes and comes, it comes in the exactly the same phase. But when a gravitational wave passes through Earth, it kind of changes the size of the Earth. It's certainly very, very exaggerated on the left side, but it does change the size of the Earth in one direction. And then you can see the change in the mirrors, the lengths are not the same now. So from those, that little difference, which was 1,000 trillion times of the width of a hair, is causing this pattern, which we can detect. And this is exactly what we detect gravitational wave, which was done in 2015. Kevin, you asked the question. So this was the first black hole merger, which was seen with LIGO in September 2015. And when these gravitational waves passed through Earth, then this kind of signal was seen on both the LIGO observatories. So that's how we study the universe. So now I have given all the tools, how we study these kind of events, all these explosions, extreme of universe, exotic, restless universe. So let's come back to our story. Then in 2017, we saw in the Hydra constellation, in a galaxy NGC 4993, 144 million years ago, when dinosaurs were still dominating the Earth, this event happened. And I have to say that in astronomy, everything you are looking at is in the past. Even the sun rays take 8 minutes to reach to us. What does that mean? So that means, suppose there is a planet at 100 million light years away from us, and they have infinite sensitivity and amazing resolution, and they can look at the Earth. They will be seeing dinosaurs. They don't know that we are there on Earth, because they are looking at how Earth looked 100 million years ago when they observe it today. So we are seeing everything in the past, and that's amazing to realize when you see that, what we know about our universe is every single thing is in the past. So that's what happened 100 million years ago. This event happened, gravitation, the two neutron stars merged. They kept traveling. Even when they reached as far as Andromeda galaxy, which is the closest galaxy to Earth, that's 2.5 million light years away. It means 2.5 million years earlier, the humans were still in the Stone Age. We were using these stone tools to survive. And by the time it reached the edge of Milky Way, which is 100,000 years from today, there were multiple species of humans. Nobody was ready to study a gravitational wave event. So so many events may have passed. I would even go ahead and say that by the time it reached Proxima Centauri, the nearest star to us, LIGO was undergoing an upgrade, and it was still not capable of detecting this kind of event. So 2015 is the first time LIGO detected gravitational wave. And then in 2017, we detected this event. And the amazing part of the story is that we didn't just detect in gravitational wave. We also detected with the gamma ray telescope Fermi in very, very high energy. And the Fermi event was exactly 1.7 seconds after the gravitational wave. So the chances of coincidence is very little. It was in the same part of the sky. Optical telescopes started looking for the event, and in NGC 4993, this event was seen. And this event actually vanished within 14 days. But those couple of weeks were good enough for all the astronomers in the world to come together, take all the spectra they could take in optical, infrared, ultraviolet bands, and all the light curves, and study them. But the story doesn't end here. As I said, we have radio bands and X-ray bands. All the radio and X-ray telescopes also observe. The X-ray detection did not happen until 9 days. First 9 days, there was nothing. And that also tells us something about the physics. Even when the optical was there, there was no X-ray. And X-ray kept brightening. It was, I think, 100 days after the event, and X-ray were much brighter. The radio was not there for 2 weeks, first 2 weeks. Optical was there. We saw it. It was gone, and radio still hadn't come. But we didn't give up. We kept looking at it. And then finally, we saw the radio emissions from the event and multiple telescopes. Not just that, the most amazing part came from the radio. There are this array of telescopes all across the US continent. It's called Very Long Baseline Array, which means it has a very, very fine resolution, less than milli-arc-second resolution. And when we observed on 2 different days, we saw how far away it was from the original position, and we could see that it's moving with 99% speed of light. And that was very, very crucial, because now all of these studies put together, it told us a lot of things. First thing, when you see Fermi and LIGO almost together, we learned for the first time that gravitational waves also move with the speed of light. We didn't know, we just thought about it. Einstein just, derived it, but theories have been proven wrong so many times. Second interesting part was that we knew that massive stars make up to iron, but we didn't know how much more heavier elements like gold, platinum are made. But by studying optical infrared, we knew that most of the heavy elements are synthesized in these mergers. Let me just tell you that as much as 10 Earth equivalent of gold and platinum was synthesized in one event. If it was here, you imagine how much richer we all will become, but that's not going to happen. And then, of course, the radio showed us that there is a jet. It means these mergers produce gamma ray bursts. Again, these were all theories. But now we had, by studying this event in multiple wave bands, we learned so much about this event. So I would just say that this one event which told us that it's a neutron star merger, it actually was like, it's an event which keeps on giving, because we learned so much from this event. We confirmed so many theories. Einstein postulated gravitational waves in 2015, and he thought he has made some mistake. He sat on it for 20 years before he said, I can't get rid of gravitational wave from my equations. And still he never believed that it can be detected, because imagine 1,000 trillion times of a hair width. But then the marvel of technology and marvel of science that we have been able to detect this, and LIGO has been detecting black hole merger events every left and right. So we are reaching one more step closer to understanding our universe, but I should also say we are still quite far away, because if you look at our universe, this is how our universe looks. We are scratching only, when we are looking at all the telescope, we are looking at this yellow part. 25% of our universe has dark matter, which we know behaves like gravity, but we don't know what that is. People have been working for decades to understand what dark matter is. Then we have universe, which is like 73% is dark energy, which we don't even know what properties are there. We know that it is the one which is causing expansion of universe because of the supernova study. We have found that. So we are way far away from understanding universe, but we are trying our best to study one step at a time. Thank you so much.
Questions? Yeah, sure. Yeah, so I. Oh. Into that. Yeah. Yeah, so I gathered that you've got two neutron stars orbiting, and they're producing a ripple, and everybody sufficiently powerful gravitational telescopes are seeing that. And so it gives a heads up on when the event happened. But I'm wondering, could you tell us a little bit about the time scales? I mean, you mentioned, I didn't look closely about those time graphs or whatever, but
yeah.
When did we make a prediction? How far in advance did we say, hey, the orbits of these neutron stars are converging on each other, and we think they're going to merge X time, and how precisely did we know that, and when did we know that?
So first of the one thing, so things are a little bit different when it's black hole versus neutron star.
Okay.
Black hole, when the gravitational waves are much more stronger, because black holes are much more massive, they're much more compact, and they have much higher gravity. So so what happens, the inspiral period and the merger. So it's very, very short for black holes. In neutron star merger, the amplitude is much less, because the gravitational force is not that large as compared to black hole. But since the gravitational force is less, the inspiral happens for much longer time. So even though the amplitude was much less, it happened for 100 seconds, the inspiral phase total signal. So it was a 30 sigma detection. When it comes to when did we know in advance, it's not that easy, because there are a lot of algorithms and softwares which are working to find these events, and there are a lot of false alarm signals, also false alarms, because the reason is that the noise is always so much larger than the signal, so they have so much of match filtering. So when the LIGO keeps recording these events, and then the software keep running, and then they do the match filtering, remove, and then they see if the signal was same in Hanford and Livingston, and also the Virgo in Italy. and then they come up. So it's never like I knew, oh, it's going on for 100 seconds, and after 3 seconds, I know, let me watch this in spiral. You don't get to do that.
Well, so the reason I bring it up too is because you mentioned at the outset that there were, thousands of authors on that paper, 4,000
Yeah.
authors, and it seems like that requires a certain amount of coordination to say,
It does, it does.
let's start looking at it. How many of those observed prior and through the event, and how many, you said, I saw the evolution of the thing like weeks, well, at least 17 days
Yeah.
after the event. So, it requires coordination to get everybody
That's-
doing that.
that's
So was it
true.
days or?
Yeah, so I have to say that thankfully the physics is such that in radio and X-ray you can wait for a few days. Radio and X-rays are non-thermal, so they are afterglow of the event. The gravitational wave event and gamma rays, they're coming at the time of merger. But these Fermi and LIGO, they have a way to send out automated alerts. So you can, if you sign up for that, even you can sign up, then you get it on your cell phone and or whichever way you want to, or so you get the alert. Now the most important thing is optical telescope, because you are going to get the event very, very fast in optical band within few hours. And then you have to see which part of the earth it is night. So there are at least 100 MOUs or more, if not more. And so different countries, telescopes, when these kind of things happen, all other observations just stop, and then you start looking for. So this one was the error circle in the sky was like 30 square degrees. So then the telescopes are looking at each, multiple telescope if they can find something. And the thing is that the event can also be from a supernova or from an asteroid or some other transient. So they have to also rule out those things. And so it does take a lot of coordination, lot of working together, and competition is not the way. Collaboration is the only way to go ahead with these things. Yeah.
Okay, thank you.
Yeah.
Question, Jim?
It's a two-part question, really. First, is it just Chandra or is it Chandrasekhar?
No, not Chandrasekhar.
Okay, okay.
Just Chandra. I'm not
Okay.
related to him.
All right.
Yeah.
Too bad. Anyway, his loss. Okay. If you were one AU, 93 million miles away from that neutron star merger, what would happen to you? Would your body just see it? Would you feel nauseous, or would you be ripped to shreds?
You have to be, I had done this calculation, you have to be around 30 to 40 parsecs away for you to evaporate. 93 million miles is, you're quite fine. You're not going to have, yeah, you're good. Yeah. Yeah.
The event that you had last month that originally was thought to be a neutron star merger, you said was actually supernova. Was that in the Large Magellanic Cloud, or where was it located?
No, so that's the thing. It was, so this event was 40 megaparsecs away, which is around 144 million light years. That event was 400 megaparsecs away, so 10 times farther away.
Okay.
Now the thing is, now one has to remember, so none of these things are happening in our galaxy or satellite galaxy or nearby galaxies. One has to remember that when we see the gravitational wave, we see the amplitude of gravitational wave. But since you all do look at the telescope, when you get the flux from a telescope, it's 1 over distance square. So if the gravitational wave amplitude is 10 times fainter, the electromagnetic signal will be 100 times fainter. So one, it was very, very difficult to see this. So first we were actually not really expecting initially, but the way it works is that what LIGO puts out, it puts out a chance probability. So it puts out fraction percentage of black hole merger, percentage of neutron star merger, percentage of terrestrial event. So this one was 30% neutron star merger. And from this data, they were saying that one of the neutron star is less than 1 solar mass. Now, it is for theorists to scratch their heads and find out how to make a less than solar mass neutron star, because we know that neutron stars are around 1.4 times mass of sun. But keeping that apart, as an observer, we didn't know how a less than solar mass neutron star will behave. So we were hoping that maybe there is a chance of detection. That's why all the telescopes started looking. And the team I work with, which is this growth team at Caltech, they have this telescope ZTF, Zwicky Transient Factory, and they were looking, and they finally, after removing all the terrestrial objects, we have 68 transients, which are new stars. And out of that, there was one which was matching with the redshift, which was put out by gravitational wave. And that's when we started following, and it was changing its flux very fast. But after a few days, it started to re-brighten again. And that happens in the supernova shock cooling kind of thing. So that's when we learned and that this is not good enough.
1A supernova or a type 2 supernova?
Type 2b. Yeah.
I've got to get a feel for the timescales of these events. For example, a neutron star merger. What's the timescale from the time you first start detecting gravitational waves to the time they actually merge?
So that's what I said. In this particular case, the signal was 100-second long.
100 seconds.
Yeah.
And what was the approximate frequency of the thing, say, just before the merger?
Just for the merger, do I not have the I don't remember at the top of my head, but I should have the frequency somewhere. It's at a higher frequency than, I've not put it down, but it's within the, so we call it listening to the universe in gravitational wave because it falls in the frequency range which our ears are sensitive to. But I don't remember the exact frequency at the time of merger right now at the top of my head.
Okay, thank you.
Yeah.
You said that you're looking outside the galaxy. So why aren't we looking inside the galaxy?
Because if you look at the physics of massive stars, there are very few stars which are as massive as 10-20 solar mass, which will explode as supernova. So if you look at the rate in a galaxy, per galaxy, the regular sized galaxy, there should be around one supernova every 100 years. But since our universe, visible universe, or the universe we know has 200 billion galaxies, we know that the chances are better if you keep looking at all the galaxies. It's just a chance coincidence. Yeah.
Get it back, two more people. Mike, right?
Yes, thank you. Do we know why the delay between the gamma rays and the gravitational wave detection?
So yes, we do actually. I didn't talk about that, but the thing is, I remember I said that these are very collimated events. So you get to see only and only when it's pointing towards us. By studying the gravitational wave signal and X-ray and radio signals, we learned that this event was not exactly pointing towards it, but 20 degrees away from us. Like if this is Earth, and then this was just a slightly 20 degrees. So it took, and so when the gamma rays came out, it took us that little time to come in our line of sight because the jet also spreads with time. Whereas gravitational wave is not collimated, it just comes out. So that's why, yeah.
Forward to right here.
Thank you. So a little more conceptual, but like for something accelerating and like it's however many light years away, but if it's accelerating toward it and like time is passing, then like would, as it comes toward you, as it's at less of a distance in light years away, would like the passage of time as you watch it like be accelerated somehow possibly?
So the time dilation effects are all like, so when we plot these things and when we tell you that this is what happened, we do take care of all these relativistic effects, time dilation and length contraction and relativistic beaming. Everything is taken into account in the calculation. Yeah.
Two more people.
So just relaying less a question and more a expression of gratitude from Michael Overacker online. quote, "Thank you, Dr. Chandra, for a riveting and excellent presentation. This is an area that I speak of often in my outreach programs. I thoroughly enjoyed it."
Thank you.
Thank you, Mike.
Thank you.
You have a question too? Oh, okay. I had a question. So I guess I was very surprised you said, not that I know a lot, but I was surprised when you said that the light waves reached us at the speed of light, but not the X-rays and not the gamma ray.
No, it's not that they didn't reach. It's just that they was produced much later. They are called afterglow. So when the jet was launched, it is the mechanism of production of radio and X-ray. So radio is produced. What happens when this explosion happens and the jet comes out? Jet interacts with the medium. Medium has these ionized particles. So electrons, for example, these electrons have to, if you take a single simple electron, it has a rest mass of around 511 kilo electron volt. You have to bring it to giga electron volt energy to produce, in the radio band. So the electrons are accelerated. They produce something called synchrotron emission, which is a non-thermal. But the radio is also absorbed because absorption of the waves happen as lambda square and radio is lowest, so it gets absorbed. So that's how there is a delay in the production and the initial radiation is absorbed. So that's why the delay happens.
So I can sleep well tonight knowing that light waves, gamma rays, X-rays, and gravitational waves are all moving at the speed of light.
Yes.
Oh, thank God.
Yeah.
I was fascinated by one of the first things you said, which was that LIGO detected a change in length of, I don't know what it was, a half a proton diameter or something over a.
Over 10,000, yeah.
How do you get rid of all the noise? For example, just the Brownian motion from temperature, from the fact that the mirrors are not at absolute zero,
Yeah, so that's
would be way more than that.
You don't see the signal as such. That's why I said there are just so many, there are different algorithms and there are different profiles are already there, how a theoretical profile will look if an event is this big, and there are more than million such profiles, and then you try to do the match filtering and fit the profile, and then you also talk to the observatory which is 3,000 miles away from you and the one in Italy, and then you see if the physics, like for example, there was a delay of 3 milliseconds between the two events, between Livingston and Hanford. That's consistent with the gravitational wave moving the speed of light. So when you see the similar signals and then you see at different places as per the physics we know, then and that's why LIGO puts out a probability, so this one had a 99% probability of being a binary neutron star merger.
And you had a chart that shows a frequency of gravitational waves prior to the event. I think the chart said 6 seconds prior to the event, it was 300 hertz or something like that.
Did I forgot where did I
And then half a
Okay.
second before the merger, it was, no, then it was 300 hertz. It was 100 hertz.
Okay, okay,
So that suggests you're already getting
not
Oh.
here.
a time series on the data. Right there it is.
Yeah.
So we're
that's
looking
right.
at 50 hertz or whatever, 6 seconds prior to merger.
Okay, yeah.
So I assume this was extracted. Like what actually set off the alarm that, hey, a merger is coming? And how many seconds prior to the merger did that alarm go off?
So as I said, this is not the full thing, total duration of where the signal is started to behave differently than, then I would say interference pattern when you will have exact same length was total duration was 100 seconds. Most of it was in spiral. And then there are very short duration. This is where merger happened for a very short duration. Type.
So is LIGO monitoring several objects that are where they already have like a tight orbit? Is it able to see continuous?
Telescope which monitors, right?
Mhm.
It's just there. It's just that Earth does this kind of oscillation, so does the
Mhm.
mirrors or the length, because Earth size is changing, space itself is shrinking and expanding. So, yeah, yeah, exactly. Yeah. So you don't know, and that's why it's very difficult to see the position. But how we see the positions are that when we see, I said 3 millisecond delay. Now, if it is like this part of it's coming from this part of the sky, then it should take this much time.
No, I'm not, I know how you got positioned. My question was, is LIGO always seeing some oscillation
Not always.
of the
when-
gravity or space-time field? Or-
Not always,
How-
because it depends on its sensitivity. Currently, they put out a sensitivity of 200 megaparsecs to see neutron star mergers.
Hmm.
They cannot see anything beyond that. Similarly, they have a sensitivity for black hole. LIGO also doesn't work continuously. It has, right now it is in 04, which is the 4th operation phase. So they work for a few months, and then they shut down for several months for the upgrades and make their sensitivity better, and then they come online again.
Hmm.
So they are looking for events only at that time when they're on, but number of events are not that many that there are multiple overlapping at the same time, because we don't have that kind of sensitivity. Yeah.
I saw somebody else had a
Are you,
question.
No, I'm good.
you good?
Yeah.
All right. Anybody else? Any last questions? Yep, right here.
How come the LIGO arms have to be so long?
Because if you have, say, 20-meter arm, how will you see that tiny change? Because even with 4-kilometer arm, you are only seeing this 1/10,000 width of a proton, right? In fact, the next generation detectors, which people are talking about and trying to get some funding, they're talking about 20-kilometer arm or 40-kilometer arm. So you have to have as big as possible. Yeah.
Last call, questions? Everybody? Well, that was fantastic. I gotta say, that was definitely. Normally at this time, I'd reach over and grab the Charlottesville Astronomical Society cup, which I didn't bring, but I will get it to you because I know you're close by here. So I'll send you an email and we'll work on that. But this was great. Appreciate your time and all your effort on this. This was really fascinating. This is fun. And what we'll do is when we finish with the uploading the video, we'll send a copy to you and ask you if you'll let us put it on our YouTube page
Sure,
with
that's
all the credits to you. Is that good?
fine.
All right, well, thanks so much. Appreciate it. All right, so